Good day and welcome to One-on-One Maths Private Tutors. Today we are looking at O-Level and IGCSE Pure Physics. The topic is the DC motor. A DC or direct current motor is an electric machine that converts electrical energy into mechanical energy or rotational kinetic energy using the motor effect. Common home devices that use an electric motor are the vacuum cleaner, the fan, the washing machine, and the blender. Any electric device that has movement uses a motor. In the previous topic, we learned that a current flowing in a magnetic field experiences a force. We also learned that a current carrying conductor in a magnetic field experiences a force. The force may lead to a turning effect on a current-carrying coil in a magnetic field because of the forces acting on the two sides of the coil. The magnitude of the turning effect is increased by increasing the number of turns on the coil, increasing the current, or increasing the strength of the magnetic field. This turning effect is the basis of all electric motors, from the electric toothbrushes to ship propulsion. The motor effect shows that a straight current-carrying wire in a magnetic field experiences a force. If the wire is wound into a coil, forces act on both sides of the coil, and a turning effect results when the coil carries current in a magnetic field. Turning effect on a coil. A rectangular coil of wire mounted on an axle which can rotate between the poles of a magnet may experience a turning effect when a direct current or DC is passed through it. The turning effect increases if the number of turns on the coil increase, the current flowing in the coil increase, or the strength of the magnetic field increase. The larger the turning effect on the coil, the faster it will turn. Now let's look at a simple DC electric motor. A simple motor to work from direct current consists of a rectangular coil of wire mounted on an axle which can rotate between the poles of a C-shaped magnet. Each end of the coil is connected to half of a split ring of copper called a split ring commutator, which rotates with the coil. Two carbon blocks, the brushes, are pressed lightly against the commutator by springs. The brushes are connected to an electric supply. If Fleming's left-hand rule is applied to the coil in the position shown, we will find that AB, which is this, experiences an upward force. So AB will experience an upward force. So using Fleming's left-hand rule, the first finger, which showed the field, will be to the right. From north to south, the current is moving in that direction, which is shown by the second finger. Then the force on the wire will be upwards using the left-hand rule. And side CD will experience a downward force. The direction of the current is from D to C, which is given by the second finger, and the direction of the field is from left to right, which is given by the first finger. Therefore, this side CD will experience a downward force. No force will act on AD and BC, since they are parallel to the field. So forces will only act on AB and DC. The one is upward, the other is downward. So this coil will rotate about this axis in a clockwise direction. So this is our split ring commutator, and these are the brushes connected to a DC power source. The positive and negative. So current will be flowing around. The upward force and the downward force on the coil will rotate the coil in a clockwise direction until it is vertical. When it is vertical, the brushes are then in line with the gaps in the commutator and the current stops. So the gaps will create an open circuit and the current will not flow when this is vertical. However, because of its inertia, which means the coil is already in motion, the coil overshoots the vertical and the commutator halves change contact from one brush to another. This reverses the current through the coil and also the directions of the forces on its side. Side AB is on the right now, acted on by a downward force, while CD is on the left, being acted on by an upward force. The coil therefore carries on rotating clockwise. Let's look at an animation to see how a DC motor works. So this is the animation of the motor. The motor converts electrical energy into mechanical energy. This is our source of power. We have a rectangular coiled copper wire that is between the poles of a magnet, the north and the south. These are the split rings shown here, the red and the blue split ring, mounted on an insulated axle. So these are attached to the insulated axle and they spin with the insulated axle. The split rings are conductors that are directly connected to our coil or armature. The axle is made of insulating material such as plastic, and it spins with the split rings. Then we have the brushes. This brush labeled X rests on this red split ring, while the other one labeled Y rests on the blue split ring. Then we have our power source, which is our battery here. Conventional current moves from the positive terminal of our battery to the brush labeled X, through the split rings, and to the left side labeled AB, going in that direction, to CD, going in that direction, and then to the blue split ring through the brush labeled Y, then back to the negative terminal. Now let's look at how the rectangular coil or armature ABCD will rotate due to the interaction of the magnetic field from the magnet and the magnetic field created by the current in the coil. Now this is the direction in which current travels in AB. This is the direction of the magnetic field due to the magnet using Fleming's left-hand rule. The first finger points in the direction of the field, which is from north to south. The second finger points in the direction of current, which is from A to B. Then the force experienced by AB will be down as shown. Likewise, On CD, current is shown by the second finger, which is from C to D. Magnetic field lines is from north to south. Therefore, the force is upward. This will cause the coil to rotate in an anti-clockwise direction, CD going up and AB going down. Now, when the coil is at a vertical position, the split rings disengage from the brushes momentarily. No electricity will flow through the circuit, but the coil is already in motion. Brush Y will reconnect with the red split ring, and brush X here will connect with the blue split ring. This has a tendency of changing the direction of the current in the coil. Now current is moving from the positive terminal of the battery through X to the blue split ring and to DC, then B, then A, then back to the battery. Now again, using Fleming's left-hand rule, for CD, current is from D to C. The field lines are north to south. The force is downward. Now CD experiences a downward force. AB, the current is from B to A, and the field lines are north to south. It will experience an upward force. So this coil will continue rotating. After every half turn, the direction of the current is reversed because there is a change in contact between the brushes and the split rings. So it will continue to rotate in an anti-clockwise direction. So the split rings enable us to have continuous rotation. So every half turn, the current changes and the rotation is maintained. Reversing the current reverses the direction of rotation. Also, reversing the magnets reverses the direction of rotation. But reversing both the magnets and the battery at the same time does not change the direction of rotation. Now let's look at typical examination questions. Students are asked to suggest factors that affect the speed of rotation of a DC motor. 3 of their suggestions are listed. 1, the strength of the magnetic field. 2, the current. 3, the number of turns on the coil. Which suggestions are correct? The strength of the magnetic field increases the speed of rotation. The current also increases the speed of rotation, and the number of turns on the coil affect the speed of rotation. So all 3 are correct. So our answer is A, 1, 2, and 3. Next question, which part of a simple DC motor reverses the direction of current in the coil once every half rotation of the coil? Answer is the split rings. So the split rings will cause the brushes to disengage momentarily during rotation so that connections are changed between the split rings. So the split ring commutator is the one that reverses the direction of the current once every half turn, which is D. Next question. A commutator is connected to the coil of a DC motor. The commutator rotates and connects the coil to the power supply. Once every half turn, the current in the coil reverses. What is the name of the commutator and what is the orientation of the plane of the coil as the current reverses? The name of the commutator is split ring, and the orientation of the coil, which is this coil or that coil, we can see it is vertical and the magnetic field lines are horizontal. So we can say it is perpendicular to the magnetic field, which is D. Here, when it is horizontal, the current is not reversing because the brushes are in contact with the split rings. It is parallel here, but only when it is perpendicular is there disengagement and current reverses. Next question. Fig 7.1 shows a simple DC motor. The poles at the ends of the magnet are not labeled. State the purpose of the split ring commutator and the brushes. The purpose of the split ring commutator is to reverse the current in the coil. So these split rings are meant to reverse the direction of the current in the coil as it spins in order to maintain continuous rotation. The purpose of the brushes is to maintain supply of electric current to the coil and split rings. So the brushes here, this one and this one, maintain contact and supply electricity to the coil and the split rings. There is an upward force shown on the left side of the coil. There is a magnetic field in the space between the ends of the magnet. State the direction of this magnetic field. Explain how you determine this direction. Since this is a positive terminal, the direction of the current is from positive, so it's moving in that direction in the coil. So using Fleming's left-hand rule, so considering this side, we are given the direction of the current, which is that direction, and the direction of the movement, which is upward. So holding our left hand thumb to represent the movement, second finger to represent our current, the first finger will point in that direction. So our field, we have our north there and our south there. So that is the field direction. So this is the direction of the field. So we can say this one is our north and this block is our south pole. So to answer the question, state the direction of this magnetic field. So it's from left to right. Explanation is using Fleming's left-hand rule, holding the thumb, first finger, and second finger at right angles. The thumb gives direction of motion. So if the thumb gives the direction of motion, which is here upwards, the second finger gives the direction of current, which is from here to there. The first finger will point left to right, which is direction of the field. State what happens to the rotation of the coil if the magnetic field and the current in the coil are both reversed at the same time. If we reverse this current and we reverse the poles of the magnet, the rotation will still be clockwise. it will remain. But if we change only the current or the magnets, then it will reverse into an anti-clockwise. So now we can say the rotation will remain clockwise. In Fig 7.1, the coil is horizontal. The force upward on the left side and the force downward on the right side are each 2.3 newtons. The distance between the sides of the coil and the axis is 0.15 meters. Calculate the total moment exerted on the coil by these forces. Give the unit of your answer. The axis is the pivot, 0.15, and is 2.3. So the moment due to this 2.3 newtons is 2.3 times 0.15, and the moment due to this 2.3 newton force is 2.3 times 0.15. So the total moment is 2.3 times 0.15 plus 2.3 times 0.15, which is 0.69 Newton meters. So 0.69 is our answer, and the unit is Newton meters. Explain why the turning effect becomes smaller as the coil becomes more vertical. As the coil becomes more vertical, the coil enters weaker magnetic regions. So this reduces the force on the current carrying conductors. So we should understand that the magnetic field is strongest at the center of the magnet and weaker as we move away from the center of the magnet. So as coil enters weaker magnetic regions, the turning effect becomes smaller. Let's look at this question. Fig 6.1 shows the structure of a simple electric motor. The current in the coil causes the coil to rotate. A student notices that the coil turns in the direction shown by the curved arrow in Fig 6.1. This direction, so it's clockwise rotation. State what happens to the motor if a stronger magnet is used. The coil turns faster. On Fig 6.1, mark and label the direction of the current in the coil. The current is moving from the positive terminal of the battery through the carbon brushes to the split ring commutator, then here. So we can show this direction there of the current. So current is going up here, around here, and then back to the negative terminal. The direction of the magnetic field. So the direction of the magnetic field is from north to south. So we can label this current and we can label this magnetic field. So we have marked and labeled direction of the current in coil, direction of magnetic field. Explain why the coil turns. The coil turns because a force is exerted on a current carrying conductor, which in this case is the coil, by the magnetic field of the magnet. So on the left side we have an upward force, and on the right side we have a downward force, but we don't have to show it on the diagram. So on the left, an upwards force, and on the right, a downward force is exerted. With that, we come to the end of the section. Thank you.